Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1861, a period of ferment in both the political and intellectual spheres, saw the publication of Karl Weierstrass' seminal work on functions which have definite derivatives. This treatise, a cornerstone in the evolution of mathematical analysis, represents a departure from the intuitive geometric approaches that previously dominated calculus. It instead embraced a rigorous arithmetical foundation, a shift that profoundly impacted the understanding of functions, limits, and continuity, and ultimately reshaped the discipline of mathematics. Prior to Weierstrass' contributions, the notion of a derivative, a fundamental concept in calculus, often relied on geometric intuition. Mathematicians, including luminaries such as Newton and Leibniz, relied heavily on the concept of infinitesimals, infinitely small quantities that were implicitly assumed to allow for smooth transitions and the drawing of tangents. This approach, while yielding powerful results, lacked the precision demanded by a truly rigorous framework. The lack of a solid foundation manifested in paradoxes and inconsistencies, especially in grappling with the properties of functions. Bolzano, for instance, had already hinted at the need for greater rigor in the early 19th century, demonstrating the existence of continuous functions that were, nonetheless, incapable of being differentiated at any point. Cauchy advanced the field by formalizing the definition of a limit, but his approach still relied on geometric arguments and lacked the arithmetical precision that Weierstrass envisioned. The stage was therefore set for a fundamental rethinking, a move away from geometric conceptions. Weierstrass, in his 1861 paper, provided this rethinking. He accomplished this through a meticulous arithmetization of calculus, defining fundamental concepts such as limits, continuity, and derivatives solely in terms of real numbers and rigorously defined operations on them. This approach discarded reliance on geometric intuition or the problematic concept of infinitesimals. At the heart of his method lies the no-familiar epsilon-delta definition of a limit. This definition, typically presented as the limit as x approaches c of f of x equals L if for every epsilon much greater than 0 there exists a delta much greater than 0, such that if the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon, provided a concrete, arithmetic means for defining and proving the existence of limits. It thereby removed the ambiguity inherent in previous approaches. The consequences of this rigorous approach were profound. Weierstrass' use of the epsilon-delta definition allowed mathematicians to define and study functions with unprecedented accuracy. This led directly to the development of much deeper understanding of function behavior. Specifically, the paper carefully examined the relationship between differentiability and continuity, and provided some of the most striking examples of functions that are continuous everywhere but differentiable nowhere. These counterintuitive constructions shook the foundations of prevailing mathematical assumptions and forced a re-evaluation of common understanding. The function that is continuous everywhere and differentiable nowhere, a function defined by an infinite summation of cosine functions, provides a prime example of Weierstrass' rigorous approach. The function's existence serves as a profound counterexample to intuitive notions that continuous functions must be differentiable, or at least differentiable at most places. The immediate impact of Weierstrass' work was demonstrably transformative. It provided a rigorous framework that allowed for the precise formulations and proofs of theorems in calculus and analysis. His approach to analysis directly influenced the teaching of mathematics. Previously, intuitive concepts had to be defined with meticulous precision through the rigorous formulation of limits and continuity. Weierstrass created a language of mathematics that was universally accepted. This language became the foundation of all subsequent developments in analysis. His work also provided a toolkit for exploring more complex aspects of functions. Mathematicians now had a foundation to discuss the behavior of functions with confidence. The immediate impact was the removal of ambiguity, the establishment of a common language, of the foundation for further explorations. The influence on functions which have definite derivatives extended far beyond the immediate circle of mathematicians. Weierstrass' approach, embraced and expanded upon by his students, including Georg Cantor, led to the development of set theory. Cantor's work on infinite sets, building directly on the arithmetical rigor Weierstrass introduced, revolutionized the understanding of infinity and the foundations of mathematics. Another student, Sofia Kovalevskaya, used Weierstrass' methods to make important breakthroughs in partial differential equations. This illustrates the broad impact of Weierstrass' approach. The legacy of Weierstrass' work is enduring and multifaceted. It forms the bedrock of modern analysis, influencing every area of mathematical endeavor. The epsilon-delta definition, once a radical departure, is now found in every introductory calculus textbook. The insistence on rigor and precision, which Weierstrass championed, continues to guide mathematical research. From the study of functional analysis to the development of modern physics, the principles laid out in his 1861 paper remain crucially relevant. Weierstrass' work provided the necessary framework for studying functions, limits, calculus with the precision the existing tools could. Weierstrass' work also has a fascinating history of critiques. Though his work was generally well received by mathematicians pursuing rigor, it was initially met with some resistance, particularly from those accustomed to the more intuitive, geometrically oriented approaches. There were criticisms that the epsilon-delta approach was overly abstract, at a distanced mathematics from its roots in natural phenomena. However, as the benefits of rigorous analysis became clearer, these critiques gradually faded. Instead, his work became a standard that was to be met by all who followed in his footsteps. His framework was adopted and became the standard for approaching calculus. The influences on Weierstrass' work are complex and can be traced to various sources. While Cauchy laid some of the groundwork in defining limits, Weierstrass meticulously built upon, refined, and generalized Cauchy's ideas. Bernard Bolzano's insights into the properties of functions, particularly his demonstration of functions that were continuous but not differentiable, provided an important motivation for Weierstrass' work. The work of Niels Henrik Abel, who had also questioned the validity of using infinite series without careful consideration of their convergence, likely had an indirect influence. Weierstrass certainly integrated these ideas into his work. These mathematicians, through their explorations and critiques, provided the intellectual environment that made Weierstrass' work possible. The direct influence of Weierstrass' 1861 work on subsequent mathematicians and their work is also readily apparent and profound. Georg Cantor's groundbreaking work on set theory, as previously mentioned, directly resulted from Weierstrass' rigorous approach to limits and continuity. Cantor's concept of transfinite numbers, which arose from his investigation of the cardinality of infinite sets, would have been impossible without Weierstrass' arithmetization of calculus. The rigorous approach introduced by Weierstrass led to the development of modern real analysis, a further refinement of the discipline in the field of physics. The methods developed by Weierstrass indirectly laid the groundwork for the development of quantum mechanics. For example, the concept of Hilbert spaces, which are fundamental to quantum mechanics, relies on the concepts developed in real analysis. The work of Weierstrass was not only a significant event for the subject of mathematics, but laid the groundwork for a wide range of fields. In conclusion, Karl Weierstrass on functions which have definite derivatives stands as a pivotal moment in the history of mathematics. By arithmetizing calculus, he provided a rigorous foundation for the study of functions, limits, and continuity. His work replaced intuitive approaches with a precise, arithmetically grounded framework. The widespread influence of this work is clear in the creation of set theory and the development of real analysis. Its rigor still guides mathematical research. The legacy of Weierstrass is enduring, a testament to the power of rigor and the enduring importance of defining the foundations of mathematics with meticulous precision. His work remains vitally important and is the foundation for the mathematical landscape we see today.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.